All right, the foundation of probability. So this is going to be a very simple video about probability, which is obvious, but um, in many debates, like philosophical debates and looking at quote unquote paradoxes, it seems very obvious to me that people don't really understand what probability is like at the fundamental level. So I'm gonna explain step by step, looking at the history, looking at mathematics, but the focus is gonna be using computation, using simulations to explain the subtleties that people miss. So at the end of the day, it's obvious, but the devil is in the details. So let's restate the obvious. Everyone knows what 50% means. That is, out of two trials, one is likely going to be heads, if we are thinking in terms of coin flips. Except if a fair coin can easily land tails twice in a row. So even though this notion is good, it's a very crude start. Fermat assigned the number 0.5 to heads is as likely as tails. That single move raises an immediate question, like what does 0.51 mean? If we run 100 flips out of a 0.51 coin, and that notion is already a little bit tricky, we very likely wouldn't get exactly 51 heads, even though 51 is the most likely single result. So what does this mean? So here I have some code in R. If I run it, so this is the flips, random flips. So we get 54 heads. A 0 is tails, 1 is heads. But if I run it again, now it's 46, and then it's 61. So it's all over the place. But this is 50. What if we change the probability to 0.51? Well, now we get 42, 52. So basically there's no difference. We can get 50, we can get 53, we can get basically any number around 50 and around 51, yes, but it's all over the place. So are we gonna get exactly 51? No, not really. So it's not as simple as it may seem. A probability of 0.50 implies that out of 100 trials, the successes are going to be around 50. So the ratio is going to be around 0.50, but not quite. And for 0.51, the same thing, around 0.51, but not quite. So if we look at the mathematics to try to define exactly what we mean, the classical definition is something like this, which is dividing the number of favorable cases divided by the number of equally possible cases. It's clean and intuitive, but it's circular because it defines probability using equally possible. So, it's good, but it's not quite uh, mathematically precise. 100 years later, so this was in 1800s, this is in 1900s. That is when it's finally like axiomatized, and this is much more specific, much more mathematically precise. We're not gonna look at exactly what this all means, but just to say that it took hundreds of years to get a definition like this. But the notation that I want to actually explore is this one, the strong law of large numbers. So we already saw this notation, which is the number of successes and the number of trials when n was 100, and it approximates p. So if p is 0.5, then for 100 trials is going to be around 50 divided by 100. But as we saw, it's not necessarily going to be that. But as n goes to infinity, this gets closer and closer to be the case. And at the limit, the probability that this is true, that is the ratio of uh, successes divided by trials, is going to equal exactly p. It's going to be 1, but only at infinity. So it looks something like this. This is a graph where as the number of trial increases, 1,000, 2,000, 3,000, the ratio of Sn divided by n gets closer and closer to 0.5. Here it overshoots, here it undershoots, but the idea is that when n is infinity, these two are going to be exactly the same. Of course, that doesn't happen in the real world, but this is what we mean. So I would like to actually run this. Let's run it. So this is another run. So it's close. 0.5026. So this is very, very close. Let's run it again. Now it's not so close, but still. But it depends. This is random. But what I really want to see is what happens when n is 100 instead of 5,000. So let's do this. Oof, that was pretty far, 0.6, pretty far from the actual probability that we should be expecting. Now in this case, it was exactly the same, but again, this was just luck. Now it's 0.8, so it's all over the place, basically. And if I change the probability to 0.51, that's not gonna be that much different. We get 0.49, so what we actually get is not that much different from 0.50 because n is 100. But anyway, this is basically what we mean that as n grows, the probability that the ratio is going to be exactly as a probability gets closer to 1. So this gives us a better view looking at the history and the mathematics. Probability is actually a prediction, but it's a prediction about a hypothetical infinite scenario. In reality, we never get infinite trials. We flip once and it lands heads or it doesn't, right? Uh, so in this case it's 100 trials, but we can change this to 1, and then this is tails, right? It just uh, we just got tails. That's what will happen in the real world. But what we mean when p equals 0.5 is something about an infinite situation, which is never going to happen in reality, but that's it's like an idea. So that's what probability actually is. If we look at the math, it's very clear. But there's a problem. So if we think about the randomness of 50 over 100, naively we say that two flips should give one heads and one tails. But two heads is just as possible. 100 flips could easily land on 52. Uh, and the probability, the chance of exactly 50 heads in 100 flips is actually 7.96, so around 8%. And we can see the full spread of outcomes. This is the actual distribution. So yes, the most likely is 50, but it's not 100% likely. It's not even 8% likely. And 46 is very likely, 54 is very likely. So even something like 35, it's still like not impossible. And if we look at one in particular, for example, 44, it's not as likely as 50, but it's not that unlikely either. In fact, it's half of as likely. 50 is 0.08, 44 is 0.04. And this is where it gets complicated because now we're looking at a probability of probabilities. So what does this 0.04 mean? It means that if one trial is 100 flips, then we run 100 trials. 4 of those trials we will get 44 out of 100. So this is like a probability of a probability. And if we look at 50, it's still a probability of a probability that we are going to get around 8. 8 of 100 of 100 flips. Something like that. So here's the same thing, except it's a line. And here we're looking at the proportion of heads. This is the shape it takes. And when it's 1000, it's much more narrow. So it's closer to 0.5. And as the number of trials increases, it's gonna be closer and closer to 0.5. And at the limit, at infinity, it's gonna be like 100% 0.5. Of course, that doesn't happen in reality, but this is what we will see. Like it gets closer and closer. Um, But what I wanted to check, let's clean this. So this is what the shape of what we just saw with 100. But now let's change the probability to 0.51. Run it again. So it's very similar. It's just slightly more towards the right. And if we change n to 1000, actually we need to run this again. Yeah, this is what we see, and it's more narrow and it's closer to 0.51, but we could still get like 0.50 easily. So yeah, there's a lot of variables that change this, but basically because we're talking about randomness, there is a probability that we're gonna get something like not the ideal expectation. But anyway, this is a related concept that I've seen used in like trying to analyze some quote unquote paradoxes, which is the expected value. So let's say that we get $1 for every head in 100 flips. According to the expected value formula, which is this, we get $0.5 per flip. Over 100 flips, it's $50. But will you actually get $50? Not that likely. There's only a 7.96% chance. Right? That's what we just saw. So the expected value is a misnomer. A rational agent shouldn't expect $50 in any single run of 100 flips. And we can see like how these two concepts are related, because it's all about an idealized infinity. The expected value is the average we will expect as n goes to infinity. But infinity doesn't exist in the real world. In any given trial, we will obtain $0.5, just like we will obtain 0.5 heads. That's like an idealized notion. So the expected value is an idealized prediction, just like probability, not something we should expect to obtain in the real world. So both are like simplifications of what we might obtain in reality, but not quite. So probability is intuitive, at least like in simple terms, it's obvious what we mean by 50%. But if we try to pin it down and define it mathematically, it's not so easy because it requires the notion of infinity. And once we consider that in the real world we don't get infinity, it's not as intuitive as it might initially appear. So the prediction, the expectation, and the actual outcome are related, but the relationship is never as straightforward as it first appears. So the prediction is what we will expect as n goes to infinity, right? Like 0.5, it means that as n goes to infinity, the number of trials that we're gonna obtain is gonna be half, exactly half, but only at the limit, at infinity. The expectation of what we will actually get is probabilistic. That is, there's an expectation that we might get exactly 50, but there's a probability that we will not. And what we actually get, which could be 53, it could be 48, is related to the expectation and the prediction, but that relationship is not one to one. It's not uh, exactly the same. Um, so that's it. Like at the end of the day, so what we get is just heads or tails. That's it. We in this case we got tails. But a probability of zero point 0.5 tells us something of what we will predict to happen if we somehow could run an infinite number of trials, which is not, it doesn't happen in reality. And the mathematics basically tells us exactly that, that the probability only makes sense, the prediction of what we will get only makes sense as n goes to infinity. That's it. Otherwise, to get the expectation of what will happen in the real world, we need to look at distributions, so we need to look at statistics. So that's a different topic. But the notion of probability is just some idealized prediction uh, taking into consideration infinity. Basically, that's it. So naively is very obvious, but when you look at specific paradoxes like or quote unquote paradoxes like the Newcomb's problem, where we really need to understand what we mean by a probability, we need to look into the details of what exactly that means. Um, so yeah, that's it. Leave a like if you find this useful and share this with somebody who doesn't get what probability actually means. Cheers.